Hello everyone, welcome to the class of Virtual Lab in Chemical Engineering. So from today's class, we will start experiment related to mass transfer laboratory, right? So previously we have done experiment related to fluid flow operation and heat transfer laboratory. So last few lectures we did experiment on heat transfer through radiation, convection and conduction. Now we will move forward with the mass transfer experiment, and today we will be doing experiment that is on vapor liquid equilibrium. So you can kind of categorize this experiment as a combination of mass transfer plus thermodynamics, as what we will be doing in this experiment is we will be computing the vapor equilibrium data for a given binary system, and then we will use thermodynamic models to predict the model parameter, so as we can compute the VLE data at other unknown points. Okay, so in a way one can include it into the mass transfer or thermodynamic laboratory. I would like to include it into the mass transfer laboratory, right? So let's begin today's class. So our aim here is to find the vapor liquid equilibrium, to find VLE data for a binary system, and then to check its consistency with the thermodynamic model, right? So for that we will be finding constant for Margulies equation. So we will be using Margulies equation of activity coefficient. What are the details of this experiment? I will come to that part also. But before starting, if we talk about mass transfer itself, so there are various concepts involved in mass transfer subject. So you must have studied distillation, you must have studied extraction, leaching, drying or filtration, right? So what are these things? So these are type of separation technique that we use as a chemical engineer for a product separation and purification, to which distillation is the most common technique that you will find almost in all sort of a chemical engineering plants, refineries, right? So the idea of the distillation that relies on vapor liquid equilibrium. So if you want to understand the distillation, you must have begun with the vapor liquid equilibrium theory in your mass transfer, and then you have moved forward with the distillation concept, right? So what is this vapor liquid equilibrium? So VL is a condition where a liquid and a vapor are in equilibrium with each other, where rate of evaporation is equal to rate of condensation. So if I consider a liquid at a room temperature, right? So this is our liquid. So there will be some transfer of molecules of this liquid phase to the vapor. Similarly, there will be transfer of molecules of this liquid from vapor to the liquid phase. So when we say vapor and liquid are in equilibrium, that means that rate of evaporation, molecule going from the liquid phase to the vapor phase, is equivalent to molecule coming from the vapor to the liquid phase, right? So when this condition is achieved, we say okay, this is a vapor liquid equilibrium. And why this VLE data is important? So basically this VLE data are required to design equilibrium stages of vapor liquid separation equipment, basically distillation column that we are seeing. So how this data are plotted? So let's say this VLE data is at some temperature and pressure value. So here we know the composition. I have two mixture A plus B. So I will know the composition of liquid phase, let's call it XAXB. Similarly, composition of A and B in the vapor phase, that is YA and YB, right? So at a given temperature and pressure, we have composition of liquid phase and the vapor phase. So this is one data. Now for a given temperature, if I have this composition of liquid and vapor fraction over all pressure, all reversibly, like for a given pressure, if I have a composition of A and B in liquid and vapor phase for different temperature value, that is our VLE data, right? So for that we get this sort of a plot. So for a given pressure and temperature, you might get this YX data, right? Then you know about the TXY plot also, right? then there is pxy plot. Okay, so this is how it looks like. Now this equilibrium data, what they represent the composition of mixture in vapor phase and which is in equilibrium with the liquid phase. Okay, so this composition are represented in terms of the mole fraction. Equilibrium composition are a function of temperature and pressure. Therefore the data are reported under isothermal or isobaric condition. Okay, however isobaric data is generally used for a distillation column design, because distillation columns generally operate on the constant pressure. So PXY data are more useful for a distillation perspective. Right? So what we understand that vapor liquid equilibrium data is nothing but a function of temperature, pressure, and in a way composition. Right? So what initial composition you start with it. So although these two are the main part, composition will be kind of a secondary thing. So I will come to the different sort of plots that we use for a vapor liquid equilibrium. Before that, let's understand the concept of relative volatility. So relative volatility between two components A and B represents how much of a volatile one component is with respect to the another component, right? So it is measured by comparing the vapor pressure of component in a liquid mixture. When the volatility of both key component is equal, when alpha is equal to 1, then separation would be impossible under given condition, because the composition of liquid and vapor phase is same. So we have a azeotrope formation. Value of alpha above 1, that means that separation is possible. So let's say I have component A plus B mixture. We have a data of YA, XA, YB, XB over time, over different temperature pressure condition. So one thing is we can compute the distribution coefficient, that is Ki. So Ki is equal to Yi by Xi. So this gives the ratio of how much of a relative amount of component will be present in the vapor compared to the aqueous phase, right? Now when we take the ratio of distribution coefficient of two components, let's say if I have Ka and Kb, and if I take the ratio of Ka by Kb, then I get the relative volatility of A with respect to B. So if alpha AB is greater than 1, this indicates that my A is more volatile. How we can say that? If alpha AB is greater than 1, that means Ka is greater than Kb, which indicates that if Ka is greater than Kb, that means ratio of vapor fraction to the liquid fraction for component A is more. It shows that the more amount of component A will be present in the vapor phase compared to the component B. So that means if alpha is greater than 1, our component A is more volatile, right? If alpha is more, then separation will be much easier. So let's say if you have two components, one component easily evaporates, so its relative volatility will be more compared to other component. So if you will increase the temperature, first component will evaporate, its vapor will be formed much faster, and then you can condense it out and then separate it. So for a distillation column, alpha greater than 1 conditions are needed. If alpha equals to 1, that means both component are equally volatile so we call it as a azeotrope. So if we have a azeotrope, then the separation of azeotrope becomes difficult in the distillation column. Why? Because if we have a both component have a same relative volatility. That means increasing the temperature, both component will evaporate and go to the vapor phase, right? So then you don't have a room for a separation. So when we have azeotrope component present in our distillation feed, then only distillation alone is not sufficient enough for the separation. Then we have to look for the other methods such as extraction or extraction combined with the distillation, right? Now based on the relative volatility value, we get the Px, Tx and Yx curve. So what are this curve? So this is how this curve looks like. So these are the various VLE plot. Which plot are included here? Pxy, Txy and Yx plot. So here you can see this is our Yx plot. If we this is y equal to x line and this is your actual VLE data, y versus x curve, right? So these VLE plots are with respect to one component, mole fraction of one component. So here and generally that one component is mostly component which is more volatile. So here this Yx data is for methanol. So you have methanol mole fraction in the liquid phase, methanol mole fraction in the vapor phase for a different feed composition. If we transfer this data into Txy plot, this is how the plot will look like. This is another example. Okay. So for the Txy plot, this is how you will get a two curve. One is T versus Y curve and one is T versus X curve. So this bottom line is T versus X curve while the top line is T versus Y curve. So what does it denote? How we can differentiate what this plot means? So let's say you have a mixture of a liquid which has a equal mole fraction of benzene. So let's assume this is the diagram for benzene and toluene. Okay. So you have an equal mixture of benzene and toluene at 345 Kelvin. Now, as you increase the temperature of this mixture till this point, this bottom line of this two-phase curve, which is called as this bottom line is called as bubble point, while this top line is called as dew point. So till you reach the bubble point line, your liquid will remain as liquid only. Once you touch this bubble point line, then after that your evaporation will start and you will come into the vapor liquid equilibrium zone. Now depending upon the temperature, you will get two splits. Okay, so some molecule has gone into the vapor phase, some are and while others are staying in the liquid phase, right? So composition in your liquid phase and composition in your vapor phase will change. So this point, if we draw a horizontal line at that particular temperature, when it cuts to the dew point and the bubble point, corresponding molar fraction will be Ya and this will be Xa. So this Ya and Xa are in equilibrium with each other. That will be transferred into this plot. So if you will, for a given temperature, if you will put this, let's say this is some X and Y composition, you will get some data. Similarly, you increase the temperature further, you will get another equilibrium, another Y and X value in the equilibrium, that you can put it here and you will get another data. So this is how you can correlate Tx and Yx curve, Txy and Yx curve. Similarly, in the Pxy curve, you have a reverse condition. I will show you that plot in a bit, right? Now you further increase the temperature of the system and then you come into the vapor phase region. If you are at this point, that means your system has completely, like your mixture has completely evaporated and now we are in the vapor zone. So again, since all the components are in the vapor zone, we will have a only vapor phase with an equal mole of benzene and toluene, since we started with that. But in between the vapor and the liquid phase, we have two phase equilibrium, and depending upon our temperature value, we will get that particular composition of vapor and liquid in equilibrium, right? So this is the basic concept of TXY or PXY diagram. Now if you will see, there is this link provided which gives you the animation for this TXY and PXY plot. So let me show it to you here. So if you will go into this link, this is a simulator by Learn Chemi Group. So it's a initiative by University of Colorado Boulder along with some chemical industries. Here you will find different simulators for different concepts in chemical engineering and other engineering applications, right? So you have simulators for thermodynamics as well as mass transfer, heat transfer. So these are just basic illustration. Some of them include some simulations also. Anyway, you can check it out, other concept from here also. So let's begin with what part I wanted to discuss here. So here you can see this is the PXY diagram as shown in the plot. Let's start with the TXY diagram first. So this TXY diagram is generated at a constant pressure. So this point represents my feed composition, right? So initially this is a mixture of hexane with the second component is not given here. First component is hexane, octane, yeah. So it's a VLE data for hexane and octane. So if you start with here, so let's say we start with a composition of 0.6 mole fraction of hexane and 0.4 of octane in the liquid phase. And once you increase the temperature till this point, till the bubble point line, you only have a single phase. Once you touch the bubble point line, you start your evaporation process starts, and you start getting vapor components also, which are in equilibrium with each other. So what will be that equilibrium amount? So if you will draw horizontal line to this TXY plot, where it will cut to this bubble point and dew point line, corresponding values will be your liquid and vapor phase data. As you further increase the temperature, you can see the vapor phase composition is increasing more and more till a point where you cross the dew point line. Once you cross the dew point line, all of your mixture has been converted into the vapor phase. So you don't have any liquid phase composition. Similarly, you can look at the PXY diagram. Now PXY diagram, liquid will be in the top and vapor will be in the bottom. So it's generated at constant temperature. So for a constant temperature, if I increase the pressure, at higher pressure obviously gas will condense and we will get a liquid phase. Okay. So initially at a lower pressure value you will have a vapor phase. As you increase the pressure, you will start getting liquid phase, your condensation will start, and you will start getting liquid phase. So you will have a VLE, vapor liquid equilibrium. Further increasing temperature, once you cross the bubble point line, after that there will be only liquid, so you have a only liquid phase, and correspondingly you will get a, so here it's PXY and TXY. Now if you use this composition of vapor and the liquid phase and plot corresponding YX curve, that becomes your YX curve, right? So this is the basic illustration for your understanding. Now let's come back to our explanation part, that so now how alpha plays role here. So depending upon the mixture that you have, let's say if you have a mixture which has a lower alpha value, so alpha AB is low value, so let's say maybe value of 2. Here alpha AB is high, so it's 4. Then this is how their corresponding VLE data will look like. Since alpha is lower in the first case, then the YX curve, the thickness of the YX curve separating the VLE line and the Y equal to X line, that will be small. While for the second case, where relative volatility is more, we have a more difference. So in this, between the Y equal to X line and VLE line. So how does it help us as a chemical engineer? So you must have studied the McCabe-Thiele method, where you compute the number of distillation stage for a given component. So in that, what we do, we draw one extract. Let's look at this. Sorry. Let me change. So you have one operating line for your top product, your distillate, and then second operating line for your bottom product from the feed to the reboiler part, your rectifying session. So to compute the number of stages, what we do, we start, you draw the number of steps on this operating line, right? And this is how you obtain number of stages required for a distillation. So these are the theoretical stages. Now for a same condition, for a same operating line condition, if you have a greater relative volatility, in that case number of stages required to achieve the same separation will go down, right? So you can see we can achieve same amount of separation in 3 stages compared to 1, 2, 3, 4, 5, 6 stages here. Okay. So that's a difference of relative volatility on your distillation column part. Again, there are so many concepts that can revolve around this TXY, PXY plots. So it's important to know for a separation what is the vapor liquid equilibrium data, right? So this is its importance. But then how to compute this VLE data for a different mixtures that we have? So there are 2 approaches. One is obviously experimental approach, where you do experiment at every temperature pressure conditions. At every pressure conditions, let's say we want to generate a TXY diagram at different pressures. So you do experiment at various pressure, compute this plot, and then correspondingly decide whether this how much separation is possible between our two component at various pressure. Okay, so that is one approach, and another is a theoretical approach where we use theoretical model to compute the VLE data. So here we will look at the both approach. So we'll first look at the experimental part. Before starting the experimental explanation, let's understand the concept of refractometer. So it's an equipment used to analyze the composition of a given mixture, right? So it works on the principle of refractive index. So it's an analytical method that measures the refractive index of a sample to determine its composition or purity. So what is refractive index? Refractive index N is a ratio of speed of light in a given speed of light in a vacuum to the speed of light in a given medium, right? So N is equal to C by V. It's a dimensionless number that depends on the temperature of the medium and wavelength of the light wave. So how it is computed? So this is one reference for you to see the refractometer. So let's say we have a different mixture. So one, you have this pure component, that component 1 is water, component 2 is water plus castor oil, and then third one is the only castor oil. In the refractometer, this is how its setups look like, where the incident light is passed through various polarized filters, and then at number 5 you have your sample present in the sapphire prism. From there will be some reflection of the light, and then it will be received on your receiver end, which is 6 and 7. Okay, so based on time needed for light to pass from this point 1 to point 7, its speed is calculated in a given medium, right? And from that we compute its refractive index. So N is equal to this V by N. Sorry, V is equal to C by N. So your refractive index will become speed of light in a vacuum divided by speed of light in a given media, right? So I am talking about this point. Now for a given sample, so if I have a pure component, its refractive index will be something else. If we change the component, instead of pure water, we have a mixture of water and castor oil at some composition, then its refractive index will be different. So what we do, we compute this, collect this all data, and then we calibrate it based on the refractive index value. Based on the composition, this will be refractive index value. Now once we have this calibrated data ready, we can reverse calculate that if I have a refractive index of a sample as a X amount, what will be its composition. As it said that refractive index varies with the temperature, we can have some correlation for that also. So in our experiment, what we do is, first you calibrate your refractometer by computing refractive index at various composition. So let's say you start with a A and B mixture with a 0.1% composition of A. You find the corresponding refractive index N1, N2, N3. So you will have a data of N versus percentage composition. Once you have data, then the refractometer is calibrated. Now we can use, so you will have some sort of a trend. I'm just drawing this arbitrarily. So let's say this is how our trend looks like. So once we have this sort of a data, and let's say I know the refractive index of my sample, then I can backtrack and find the composition of that material. Okay, so what will be the percentage composition of A and B? So this is to find the composition. Now in the experimental procedure, this is how your setup will look like, where you have a mixture which is present in this conical flask, which is heated by an external heater. Once the sample is heated, there will be vapor which will be forming. That vapor will go into this collecting chamber, which is jacketed by flowing a liquid water inside on the outside, because of which this vapor will be condensed, and then they will fall into this sampling part, from where you take the sample. You take this sample, you put it into the refractometer, find its refractive index, and backtrack and calculate the composition. So this is how we will find the composition of our mixture in the vapor phase. So this is how the experimental procedure follows. That first we prepare the calibration chart for refractometer. Start with a mixture of A and B. So prepare about 200 ml of mixture A and B. Now experiments should start with a mixture which is richer in more volatile component. Okay. So put that initial composition into our flask, boiling flask. Ensure the electric coil is submerged into the liquid to avoid the ignition. Switch on the power. So we start the heater. It will start increasing the temperature. Once the temperature becomes steady, so you have to wait for a few minutes, right? So this will be indicated by the constant temperature. So you start heating at some rate. You wait for a temperature to stabilize. Once the temperature is stabilized, you can say, okay, now vapor and liquid are in equilibrium. Our equilibrium has been attained. Take down the liquid and vapor sample and determine its refractive index. So we will determine corresponding XA and YA. Once that is done, so for a given composition, we have computed XA and YA. Now what we will do, we will change the composition in the feed again. So initially we started with 160 ml of A and 40 ml of B. Now change it, and let's say we put 140 ml of A and 60 ml of B. Repeat the step 1 to 5. Determine the composition at every point, and then at the end we will find the we can plot the Vx data, right? Yx data, and then or Txy data. So this is how this experiment follows. So let's look at the actual experiment setup here. Oh, I think it won't work here.
Virtual lab for binary Weber liquid equilibrium, developed by a group of IIT Guwahati faculties and students from the Department of Chemical Engineering. The first step is to log on to vlab.co.in. The second step is to click the link for IIT Guwahati on the extreme left. The third step is to click the link for virtual lab for mass transfer, and finally binary Weber liquid equilibrium. This step takes us to the online portal. The first page on the online portal is the theory tab, which gives a brief description behind the experiment. The second tab is the procedure, which gives us general explanation of how the experiment could be carried.
So I will skip this.
Nation actual data, actually is the lab calculation carried out. The first step is the calibration. The second step is virtual data. The third step is equilibrium composition determination. The fourth step is relative volatility calculations. The fifth step is the parity plots, and finally possible reasons of deviations from the standard well.
Now this setup shown in this video is from VLab virtual lab developed by IIT Guwahati. So if you will go into this reference link that is provided here, as of now this setup is not working. So for that, for the simulation setup that they have shown, you have to download some files. So it's a exe files, but what I have found, it's not working in my PC. You can try it in your PC also. Probably you will need a flash player for this setup to run, which I don't think so is currently available. So we won't be using this virtual lab. Rather, there is another virtual lab developed by this Learn Chemi group, right? We will be using that as a virtual lab part. I will come to that also. So here what we will do, we will just skip to the actual experimental setup.
Before the users are notified, then is the post experiment. When the This is the experimental setup showing the round bottom flask, the heater, the condenser,
so you can see here
and two water streams.
That in your condenser, so this is condenser tube which is inside, and outside through the condenser tube there is another hollow tube where water flows. So this is water inlet and that's water outlet to cool down the vapor which are coming from our bottom flask.
These are the two inputs, that is toluene and benzene in our case. We make a mixture of benzene and toluene and insert in the round bottom flask. Then we on the heater and let the mixture to boil. We on the tap. This supplies the liquid steam for the condenser. The other stream is the output. When the mixture begins to boil, the vapor passes through the condenser and condenses into condensed vapor. We measure the temperature. Equilibrium is marked when the temperature is steady in both liquid and the vapor phases. This is the condensed vapor which is collected. Now using the refractometer as shown, we can measure the refractive index. Now next we have the virtual wall experiment.
So this setup won't work for us, so I will skip to this. So basically the procedure that we had discussed, we repeat same here in the virtual lab, and then at the end you can plot this txy or yx plot, right? So for our experiment we will be using virtual lab by Learn Chemi group. So this is the similar setup as that was shown in the experiment, right? And here we can change the composition of our boiling flask and correspondingly compute the value of samples that has been collected in our after the condensing the vapor phases. Okay, so we will use this and generate the data. So this is the experimental aspect, but in order to understand the theoretical calculations, we have to use this experimental data to fit our theoretical models. So for that, what we will do is we will rely on some theoretical models. So here from experiment we got this Tx and Yx data. So let's say this is how our data points looks like. But this won't be exactly like the smooth curve or continuous line. Rather, we will get some data points. For a different composition. So it's not a continuous line, but we have this discrete point which kind of forms this envelope. But based on this information, if I want to find the composition, if I want to find the TXY data at, let's say, this temperature value. So here I don't have any corresponding data, right? So in that case, we have to use this experimental data to fit into some sort of a theoretical model so that we can compute the VLE data at other conditions. So for that we will rely on the theoretical models. So as you all know, the Antoine's equation gives us the vapor pressure of a component at a given temperature, right? So if you know the Einstein parameter for a component, then you can compute its vapor pressure at a given temperature. Now, the Raoult's law, which is an ideal representation, states that for a vapor liquid equilibrium, we can write YIP, which is mole fraction of a component in the vapor phase, into its total pressure value. So this is nothing but a partial pressure Pi is equal to YIP is equivalent to mole fraction of component into the liquid phase into its vapor pressure value, right? So this is Raoult's law, which works assuming the ideal condition. But for a non-ideality, there could be non-ideality in the liquid phase, there could be non-ideality in the vapor phase also. Now at the condition that we are operating, so which is generally at a low pressure, main non-ideality will come in the liquid phase part. For a vapor vapor phase to behave non-ideally, generally higher pressure conditions are required, where the interaction between molecules or interaction between the air molecules or air atom becomes much larger in the magnitude, right? So for a VLE conditions, there will be the non-ideality in the liquid phase is more prominent. So for that, we include the non-ideality constant in a modified Raoult's law. So that assumes that liquid vapor phase follows the ideality. Liquid phase, you have this activity coefficient for a given component. So this is our modified Raoult's law. Let's say if you want to include the non-ideality in the gas phase also, then we include the fugacity into the picture, right? So this is for like non-ideal system, where non-ideality in both the liquid and vapor phases are. But for our condition, we will consider modified Raoult's law, which considers non-ideality in the liquid phase. So if I have some composition data xi, p site I can calculate from the Antoine's equation. Total pressure is known, so we are doing experiment at some constant pressure. Then I can compute the corresponding vapor composition if we know the activity coefficient of that component. To find the activity coefficient, so this activity coefficient are nothing but it relates the non-ideality of a given mixture. So that are computed based on various thermodynamic models. So you must have heard UNIFAC, UNIQUAC, then there is this Margulies model, you have NRTL method. So this all methods are used to find the activity coefficient of a given mixture, of a given component in a mixture, right? So we will be using Margulies activity model, which relates the excess Gibbs free energy of a mixing to Margulies constant and the liquid composition. So what is this excess Gibbs free energy? So if we have an ideal mixture, ideal liquid mixture of A and B, so ideal mixture assumes there won't be any volume change when two liquids are mixed, there won't be any heat of mixing, but due to the non-ideality there will be change, there will be heat of mixing, so we will get the excess free energy, right? So this Gibbs free energy, which is in excess, relates to the change in the heat of mixing, right? So the Margulies activity models relates that non-ideality with the activity coefficient, the Margulies constants A21 and A12 and the liquid mole fraction. Now if we know the Margulies constant, then from there we can compute the corresponding activity coefficient. This activity coefficient can be put into modified Raoult's law to compute the corresponding vapor fraction, right? So this is how our theory will work. So here this is how the theoretical part will work. Now I'm not going into the details of activity model. Here we have selected the Margulies model, which is the simplest model. You can further refine this method by using NRTL or UNIFAC methods to compute the activity coefficient. So what we will do in this experiment is, first we will generate the VLE data from the experiment. We will use that data to find the activity coefficient using Margulies model, and then check how much error we are getting with respect to experiment, so that once we compute this activity coefficient, then we can calculate VLE data at other conditions, other unknown conditions, right? So this is how whole experimental idea is. Now let's go to the experimental part. So if you will click on the experiment link here, it will take you to the virtual lab, vapor liquid equilibrium virtual lab laboratory. So first, before starting an experiment, do a reset laboratory. When you do a reset, it restarts the experiment with some sort of some new Margulies activity coefficient parameter and generates the VLE data, right? So if I will do a reset, here you will see the endpoint parameters and rest of the thing will also change. See the molar weight fraction, the density and the component endpoints parameter change. So start a new set of experiment by resetting the laboratory. We will start with the volume. So we have two components, A and B. We have to put initially high amount of more volatile component in our boiling flux. So we will start with first pure component A. So corresponding ml of component A is 100 ml and component B is 0 since we have pure component. Now start the experiment. So for that you do collect sample. Sample will be collected and corresponding vapor fractions will be calculated. Right? Now change the value again. So from 100, let's go to 95. So now you have 95 ml of component A and 5 ml of component B in the flask. Wait for an temperature to rise, temperature to attain a steady state, and then again collect the sample. Right. So you collected the sample. Now from 95, let's go to 90 ml. Collect the sample. So here we don't have to wait for heating rate or equilibrium to achieve, since it's a simulator. While in actual experiment you have to wait for a steady state to attain first, and then we will collect the sample for a calculation part. Right? So what I will do, I will take a 5 ml interval at the both end, while 10 ml interval in between. So from 90, let's go to 80 ml and collect the temperature, collect the sample. You know the data. This data are automatically stored. We will take that data at the end. So here you can see, as I am changing the composition also, the equilibrium temperature is also changing. Right? So from 70, let's go to 60. Now how to decide this temperature? Okay, so for that, here what we are doing, once you have put the sample, let's say 60 ml and 40 ml, 60 ml of A and 40 ml of B in a boiling flask, you start heating, increase the heater input. Once you will start seeing the vapor phases, vapor component being generated, then you can stop at that point, since now the some vapor fraction has started forming, and then you can wait for equilibrium to achieve, and at corresponding temperature you note down the sample value. Right? So you don't have to be exactly at some temperature. Once you notice, okay, now vapor fraction has started forming, now vapors have started forming in our system, and we got some amount of condensate, and then you can wait for equilibrium to achieve at that point. You don't have to change or increase the temperature by changing the heater rate. Okay. Fine. And now pure component B and collect its sample. Okay. So we have collected all the samples. If you will go into the documentation, you will find some theory, video instruction on how to use the virtual lab and how to find the activity coefficient parameter. We will go into this calculation part also. Various equations that has been used in the calculation. So here what we are doing is, anyway I will come to this calculation part at the end. Right? Now once we have taken out the samples, download the measurement. Let's save this file. So these are our experiments data. You have Antoine's parameter for component A and B. Right. The pressure value, so it was done at 1 atmosphere, experiment 760 mm at its 1 atmosphere. Initial composition that we put into our boiling flask, and corresponding vapor fraction that we observed at a temperature values. at equilibrium temperature value, right? So let's go to the calculation part. This Excel sheet will be provided to you for the calculation. Okay, so there are various references for you. As I said, once you will reset the laboratory, next set of results will be generated based on new Margulis parameter for a newer component data of A and B. So you will get different values at every time, and there are various reference calculations for you that are provided to you. So let me create one copy for our current experimental data. I will discuss each calculation part in detail. So this is our data. First, note down the molecule weight of component A, component B, their densities. Then endpoint parameters for component A and B. Pressure values known. Now our initial sample starts from so we have initially 100 ml of A and B is 0, then 95, 80, so 95, 90, 80, 70, 60, 10, 20. So I'm just copy pasting the data that we collected. So first we have a molecule weight and the density for our components. So we will first find the molar density of this component. That is computed by doing density divided by the molecule weight. So we will get the molecular density for both component A and B, right? So density divided by molecule weight for component A and component B. This will be used to compute the liquid phase composition, that I will come in a bit. First, let's find the just from the experiment itself, we would like to plot the YX and YX diagram and TXY diagram, since it's a constant pressure experiment, right? So we know the Y value, but we don't know the corresponding X value. So how to compute that? That we will compute from the data that we have. So we know the initial composition for our components, right? So if you will see here in the documentation, analyzing the data, yeah, this is how it is. So we know the temperature value, we will find the corresponding saturation pressure for both component A and B. Once we know that, this part we will keep it aside. Oh, sorry. The step number 6. The mole fraction of component A and B can be determined from the molar density and volume. So molar density Ca and Cb we computed. Now we know the volume of A and volume of B in the boiling flask. So from this equation, so molar density is number of moles per ml. So from that we find the moles of A. So Va into Ca will give the moles of A. Vb into Cb will be moles of B. So summation of that is total mole. and this is moles of A. So mole fraction will be moles of A divided by total mole. So this is how you compute XA and XB, right? So in our experiment, XA is computed based on volume of A into its molar density divided by total moles. So that is summation of volume of A into its molar density plus volume of B into its molar density. So this is how you compute XA to till this point, right? And XB will be again similarly volume of B into its molar density divided by total mole, or you can directly do XB is equal to 1 minus XA also, right? So here I am putting it in both. So you have XA and XB data. Your YA is nothing but it's equal to, it's taken from the experimental value. So this is your YA, and YB will be 1 minus YA. So you have, so now you know this data. So you have this VLE data at corresponding temperature value. So we can plot YX data. So here you can see this is how your YX curve will look like, where I have plotted YA versus XA. Here the curve is not looking too smooth, but if you will try to draw a y equal to x line, so this is how it will go. So you can see at a lower molar fraction of A, we have a higher, A has a higher volatility, but at a higher mole fraction, it almost coincides with the y equal to x line. So that means the separation of A and B will be much higher if we have a lower composition of A, and it will be difficult if you have a if you are at a higher composition, because your y equal to x line is almost coinciding with your VLE data. Similarly, you can plot Tx and Yx data. So this is how it should look like. So this is one plot, Yx data. So this is how our TXY diagram looks like. So again you can see at a lower mole fraction of A, we get a two-phase separation. We get the in-between region where both vapor and liquid will coexist. But at after 0.7 mole fraction of A, both vapor and liquid mole fraction line Ty and Tx lines are almost coinciding. That means at this conditions, if we have if for a 1 atmospheric pressure, if we have this composition, if we lie in this particular region, the separation of A and B won't be possible. But if we are at a lower composition, if the mole fraction of A are less than 0.6, in that case we can achieve the separation of A and B, right? So this is one basic example. We computed the Yx and Txy plot. So this is the experimental part, but these are the discrete points, right? So we know the Txy value at 64.5, then we know at 62.4. But what if I want to know what is the equilibrium composition at temperature 63, or what is the equilibrium composition at 66 degrees centigrade temperature, right? So for that we will rely on the theoretical model. So for that, first compute the corresponding vapor pressure for both the components A and B at a given temperature, right? So for that, you know the Antoine's parameter. For that, you know the Antoine's equation. You have the parameter ABC. Then you can compute the P set, that will be in mmHg. So this equation and the coefficients are such that temperature is in degree centigrade and the pressure value that we will get is in mmHg. First compute the P set for the both components. So this is the equation, I have already put it in. It's 10 to the power A minus B divided by C plus temperature value, right? So this is our equation. I have just used that one. compute the Vapour fraction for both of them. Once you do that, next step is to find the activity coefficient gamma 1 and gamma 2, gamma A and gamma B, right? Now gamma A and gamma B, for that we need liquid phase composition and Margulis constant. So initially we don't know what Margulis constant value should be. So we will start with some guess value and then compute the corresponding gamma N and gamma B. Once we have that gamma N and gamma B, okay, so which are important, we will use modified Raoult's law to compute corresponding liquid Vapour fraction. So for corresponding xi we are computing the activity coefficient. From modified Raoult's law we will compute corresponding yi, and what we will do, we will try to differentiate difference in the experiment and theoretical data to fit this A12 parameter. Let me explain it here in theory. Just a moment. So we have Y experiment, X experiment and corresponding temperature values. Okay, we have this data, this tabular form data we already have. We compute PI set, okay, then we use Margulis equation to find the corresponding activity coefficient. Okay, once we know the corresponding activity coefficient, then we compute corresponding yi. So this will be a theoretical value, right? So PI set is calculated as a function of temperature. Activity coefficient will be function of xi and Margulis parameters. So start with a guess value. Find the yi. Now our modified Raoult's law says that yip is equal to xi pi set into gamma I. Therefore yi theoretical is equal to xi pi set gamma I divided by total pressure. Okay, now we will do difference of experiment versus theoretical value square. So we will find the error square. You sum that error square for both component I and B. So this is our total error, and we minimize total error by changing A12 and A21. Okay, so minimize this total error by changing A12 and A21. So what we are doing, we start with some guess value and then we move forward. We compute the activity coefficient, we compute the corresponding theoretical Vapour mole fraction. Then we take a difference of theoretical and experimental Vapour mole fraction, find its error square, sum this total error and try to minimize this total error So by that we are changing the value of Margulies constant A12 and A21. By doing so, we are reiterating so it's a kind of iterative process. You change the value of A12, A21, then again find the total error. If error is decreasing, then you are going in a right direction. You again change the value of Margulies constant and see the error till you find that your error is within some tolerable limits. So by doing so, what we did, we fitted our Margulies parameter on the experimental data that we have. Now, since we know that this corresponding new A12 value, A12 and A21 value will give me correct or near about value to the experiment, I can use this parameter to find the VIE data at other temperatures condition also. So this is the whole concept that we are following here, right? So again, let's resume back to our calculations. Let me close this. Here. So we calculate the gamma. So this gamma initially based on some value. So currently 0.47 and 0.51 are selected as a value. You have to use this equation, right? So gamma A will be inverse exponential to the power this term. This has been already implemented here, okay? And compute the activity coefficient of A, gamma A. Similarly, compute the gamma B. Okay, so gamma B again follows the same equation that is given in the theory. Once you know, you can compute the total pressure also. So total pressure P is summation of xi gamma I pi set. That this should ideally come somewhere around 760. So that is our actual experimental condition, right? So here you can see it's varying between 760 to 650, since the Margulies parameters are not are guess value. Okay. Now corresponding Vapor mole fraction will be calculated from the modified Raoult's law. So that is xi. This is our xi value, H14, then gamma I, which is M14 into pi set divided by the total pressure, right? Sorry, here total pressure will be, since it's a constant, we have to use this value. So you can see it's, the molar fraction is coming more than 1. So that means our coefficients are not correct. Oh, yeah, here it should be taller. I need to fix this value. Similarly, you can compute this data. So this is YA and YB computed from theoretical model. So here you can see both sides it's going greater than 1. That means our guess value is not correct. Now find the difference of error square between the calculated value and the experimented value, right? So this is the error square, and corresponding total errors. So this is total error, which is summation of both errors in the mole fraction of A and mole fraction of B. Now we want to modify Margulies parameter such that this error is minimum. So for that we will use the solver option in the Excel. If you don't have a solver in your Excel, you can go into your accounts option in your options and look for advanced options and find some add-ins. Yeah, here. So here if you will search for the solver add-on, then you can import that. Okay, you can watch some YouTube tutorial how to add solver into your Excel, right? So once you do that, then use this solver to minimize the error. So here my target cell or a subject cell is total error. We want to minimize it by changing the variable. So our variable will be Margules parameter A12 and A21. So we want to change this 2 parameter. Now the Margules parameter, they have a range of, they vary between plus or minus 2. Okay, so Margules parameter vary between plus or minus 2. I think it was mentioned somewhere. It's not mentioned here, but if you will look at the theoretical part of Margules activity coefficient, you will find that it varies between plus or minus 2. So for that we have provided a conditions by adding a constraint. So if you add a constraint, you can select a cell and provide that it should be greater or equal to this value, less or equal to this value, right? So we have added that parameters and provided that okay, this parameter should be between plus or minus 2. Okay, once you do that, you can use the solve button. Solver will solve it and then you will find the corresponding new value. So you can see your error has been minimized and new parameter. So instead of 0.4 or something, I think it was 0.47 and 0.51, now you have got the value of 0.88 and 1.17, and corresponding your error has been minimized, right? Still there is some higher value in the molar fraction, but that is due to the calculation error part. If you have a more data set, then more better fitting will be done, right? But you can consider that, see, almost you are getting 10 to the power 5, 10 to the power minus 9, minus 5 to minus 9 as a error value. So that's a negligible error value. So now this new parameters are the fitted parameters. So with the help of this parameter, I can select some other temperature value and compute the corresponding vapor fractions, okay, provided that I know the initial composition, right? So for the initial composition, let's say for 90 and 10, I vary the temperature value, find the corresponding xi value, and from that we can use the Margules equation and then we find the vapor composition, right? So that thing you can also put it in here along. You can compare that with this plot and see how it varies, right? So this is one point. So here you have a discrete point in your y-x plot, right? So if you will change for xi is equal to 0 to 1, so here we have some xi value of 1 to 0.8. So you can change the value, let's say 0.01 decimal, and you want to get a really smooth continuous curve. So take out all the 0.01. So between 0 to 1, take an interval of 0.01, take all the xi value, find the corresponding yi based on the Margules equation, Margules parameter, and modify Raoult's law, and then you will get this much smoother plot compared to this, right? So this is how these theoretical models are useful to compute the VLE data. Now you can check your data by submitting an answer. So in submit answer, you can put this value. So we have got 0.881 and 1.171 and 1.171. Now there is this upper and lower limit part in the calculation which I have not shown. You can see that in the video reference that is provided here, but for our class it's not that important. So I will just put some close by value to the actual parameter, and let's see whether we have got similar results or not. Okay, So you can see here we have got some closed results. So correct value on which experiment was designed is 0.79 A12, while we have got the value of 0.88, while A21 is 1.26 and we have got 1.77. You might get exact value matching with your with the virtual lab data if you have a more data points, right? So here we have only how much, 10 and 12 data points, right? So if you will take more data points interval, then you can fit the parameter much better, and then you will get a much closer value to the data that has been used for to generation of the experiment, right? Another thing is that this solver works on the initial guess. So if your initial guess is much far away from the actual value, then solver might lead you to some different results. Okay, so that is also one point for a calculation to be considered. So let's see if we again do the solve here. No, it's not changing much, so yeah. But the bottom line is that you can use this method to compute VLE data theoretically also. Once you are done with the experiment, just reset the laboratory, and then you will start with the fresh data set, fresh A and B components and corresponding Margulis parameter. Now in the documentation, in the video instruction, you will find that 95% limit upper and lower. If you are interested, you can check it out. For our perspective, it's not that important. The Excel calculation sheet will be all provided to you, but if you still have doubt, you can watch our lecture recording, or you can also refer to the video provided by them where they show this Excel calculations. Okay, so this was from my end for today's class, where we learned about the Whipple liquid equilibrium, how to compute the VLE data from the experiment, and how to use theoretical model to compute VLE data, where we use the Margulis activity coefficient method, to find the activity coefficient, right? So that's it from my end. For the next class, I have to see what. Okay, yeah, I'm not sure what we are planning to do, but again it will be related to the mass transfer laboratory, since we are following that same trend. Okay, so I will stop the recording. If you have any doubts, do let me know.